According to the equation PV is equal to nRT, we can tell that P and T are going to be direct with each other if the volume is held constant. And this T here has to be measured in Kelvin. So we call this T the Kelvin temperature or the absolute temperature. Now, when temperature is equal to 0 Kelvin, we call that the absolute 0. And when this happens, the pressure has to become also 0. Okay? Or when the temperature is equal to negative 273 Celsius, and sometimes they might say negative 273.15 Celsius, at that point also pressure is equal to 0. That means that the gas particles or molecules will stop moving when this occurs. Now let me show you what this looks like on a graph. So right now, if we were to plot on the y-axis pressure and on the x-axis temperature in Kelvin, then basically when we have a 0 Kelvin, we also have a 0 pressure, and they will be direct with each other, which now can be represented by a straight line going up. Okay? But if I were to plot pressure on the y-axis and temperature in Celsius on the x-axis, I cannot have a 0 pressure at a 0 Celsius. No, I can have a 0 pressure at a negative 273 Celsius. That basically means I must extend my x-axis in a negative direction. I must now draw a straight line that will go into the negative part of the y-axis to hit that negative 273 Celsius. And at that point, that's when the pressure becomes 0. Okay. Now, so we had PV is equal to nRT before, where N was the mole. How about now PV is equal to NKBT? And now in this case, capital N here would mean the molecules, and the KB here will be something known as the Boltzmann constant, okay, which has the value, the Boltzmann constant, of 1.38 times 10 to the power of negative 23. Now, molecules is simply equal to mole, but simply times the Avogadro's number, which you have to know to be 6.022 times 10 to the power of 23. Okay? In both of these equations, the pressure has to be measured in Pascal. That means that if you're given a pressure in the question as ATM, it's your responsibility to multiply it by 10 to the power of 5 to convert it to Pascal. At the same time, in both equations, the volume has to be measured in meter cube, and also in both equations, temperature has to be measured in Kelvin, and also in both equations, R is equal to 8.31. Now, according to this equation, basically, we can say that if temperature is held constant, if volume is held constant, in that case then, pressure will be direct with the capital N. Okay? And the capital N is basically equal to the mole times Avogadro's number. And if you want to increase the mole of the gas, you simply have to increase the mass of the gas. That means if you inject gas in a container with the temperature held constant, with the volume held constant, you will be basically increasing the mass of the gas, which will result in the increase of the pressure exerted by that gas. Okay, now if you look at the equation sheet, we have two equations for kinetic energy. We have half mvrms squared. And vrms just means the average velocity of all the particles that are out there. And we also have another equation, which is 3 over 2 kBt. Now, according to this equation, we can say that the k and the t are going to be direct with each other. And again, this T has to be in Kelvin. It's the Kelvin temperature. Now, if I were to just equalize those two equations to each other, then I could do the following. I could remove the 2's in the bottom, end up with mv squared RMS is equal to 3 kBt. Now I'm going to isolate for the v squared RMS to be equal to 3 kBt over m, and now the VRMS is equal to the square root of 3 kBt over m. Okay, now what this shows us is that the VRMS will be direct with the square root of temperature. And by the way, here the m is equal to the mass of one atom, or the mass of one molecule, and the unit is going to be kilograms. We can also now say that if you have two gases, gas A and gas B, whose identities are different, okay, if they are held at the same temperature, then they will have the same kinetic energy. But because they have different identities and they have different molar masses, they will have different speeds. The lighter gas will basically be more fast, or faster basically. All right, let's now talk about gas particles that have been held up inside a cube. So here we have a cube, and we're dealing right now with a three-dimensional structure, y, x, and z. That's called 3 dimensions. Okay, and now we're dealing with a particle, with a single particle whose mass is m, that's going to be moving in the positive vx direction. So it's moving in the positive x direction, and its velocity is going to be called vx, because velocity in the x direction. Okay, so now let's define vx as the velocity in the x direction, and velocity is going to be a vector. That means that its sign depends on direction. So if we're going to be going in the positive x direction, the velocity is going to be positive. But if we're going to be going in the negative x direction, the velocity will be negative. Now, this is a cube, and right now we're looking at one face of the cube, which looks like a square. Maybe it's not exactly a square looking like, but it's actually a square. It's what I meant it to be. And each side of the square is going to be of L length. Okay. Now, let's follow the path of this particle as it travels to the right side, and it will be colliding with the wall on the right side, and then it will be bouncing back in the opposite direction. Okay, so basically the particle initially starts to move in the positive x direction, but then finally starts to return in the negative x direction. There is this quantity that you guys have to be aware of. That's called momentum. Momentum is equal to mass times velocity. Okay, so now we have basically two momentums. We have the initial momentum, which is going to be m times vx, because we are moving to the right side. And now we also have the final momentum, where the particle or the molecule has hit the wall and is now going to be bouncing in the opposite direction, in the negative x direction. So we're going to say negative m vx, because now we are going to the left. Going to the left makes your velocity negative. Now, there is this equation, or this basically name of a variable in physics called impulse, which is equal to the final momentum minus the initial momentum. Now, the equation of impulse is going to be force times delta t, which equals to the final momentum, which is negative mvx, minus the initial momentum, which is given to us as mvx. Okay? Now, this is the force that's basically by the wall on the molecule, which caused the molecule to bounce back to the left. And delta t is the time that it takes the molecule to go right and then to go back in the left direction. Okay? Now let's just simplify the right side. So we're going to have F times delta t is equal to negative 2 mvx. And now we can say that this is the force of the wall on the molecule. And now we can simply say that the force of the wall on the molecule is equal to negative 2m times Vx over delta t. Okay? Now, if the force by the wall on the molecule is negative, then the force of the molecule on the wall has to be positive. So the same exact equation, but simply now a positive. And by the way, this is the application of Newton's third law. What Newton's third law says is that the forces, the one going in one direction, let's say the wall on the molecule, and the one going the opposite direction, which is the molecule on the wall, will have the same exact equation, but simply the opposite sign. So right now we're going to be focusing from now on F molecule on the wall being 2 mvx over delta t. Okay, now let's bring up this new equation here, which is speed is equal to distance over time. It should not be very new to you, but if it is, then listen carefully. Right now we're dealing with the speed in the x direction only. That basically means I am dealing only with Vx. Now, distance here is to go to the right side, which is L, and then to go back, which is another L. That means that distance is going to be L plus L over the time, which is delta t, the time to go and to come back. So essentially now, Vx is equal to 2L over delta t. Let's now isolate for delta t by simply switching its place with the Vx. Now delta t is equal to 2L over Vx. Okay, now let's go back to our equation and change delta t to 2L over Vx. So now let's replace that delta t with 2L over Vx. Okay, now this is like a math property, so A over B over C would be equal to A times C over B. So we're going to say that the F of the molecule on the wall will be equal to 2m Vx times Vx over 2L. Okay, and now we can simply cancel the 2 with the 2. We'll end up with m Vx squared over L. Okay. Now, so far we've been discussing a single molecule. What if I want to discuss all the molecules that are held in this container? I must now change my equation to F of gas to include all the molecules on the wall. I must now multiply my equation by n for molecules. So now my equation is going to be n times m times Vx squared over L. Okay? But now my Vx squared has to change to Vx squared average, because right now we're looking at the average velocity of all the molecules and not just a single molecule. Good. Now we have made an equation or derived an equation that tells us the force of the gas on the wall is equal to that. Now let's talk about the equation of pressure. Pressure is equal to force over the area. So now I'm going to be saying that the pressure of the gas on the wall is equal to, replace the force of the gas of the wall on the wall by Nm Vx squared average over L, and the whole thing must be divided by the area, and right now we're looking, if you guys recall, at a square. You see, we're looking at a square because this is L and that's going to be L, and the area of the square is going to be side by side, which will be equal to L squared. So now we can replace the area with L squared, and now just like the math property, A over B big fraction over C is equal to A over B times C. So now we're going to say that the pressure is equal to one big fraction N M Vx squared average over L squared times L, which will give you L cubed. That's going to be the equation for the pressure of the gas on the wall. Now, don't forget that we're dealing with a cube, and in a cube, the volume is equal to side by side by side. That means L by L by L, and so we have L cubed. The shape is going to be a cube. Maybe it's not drawn so, but you were told when the question started it's a cube, and that's how the volume is equal to L cubed. So now it's time to go back here, and it's time to simply replace the L cubed with V. So N times M times Vx squared average over V. That's going to be our pressure. Now, so far we've been dealing with only the x direction, but guess what? Our particles are not only moving in the x direction, they're moving in the x direction, they're moving in the y direction, and they're also moving in the z direction. Now, the velocity in the x direction and the velocity in the y direction and the velocity in the z direction will all be the same. Okay, by the way, this v here is not velocity, it's volume, just for you to remember that. Okay, now, so Vx and Vy and Vz are equal to each other. Since we're dealing with a three-dimensional shape, we must be dealing with something called the super Pythagorean theorem, which would say that the hypotenuse is equal to the first side squared plus the second side squared plus the third side squared. Right now, if you square everything here, you will get hypotenuse squared is equal to a squared plus b squared plus c squared. How does that translate to our equation? Because now we can say that Vx squared plus Vy squared plus Vz squared will be equal to V squared. And of course, right now we're dealing with the average velocity. So just add the word average to all of them. Add the word average to all of them. Now, as you were already told, Vx is equal to Vy and is equal to Vz. So now we can replace the Vy and the Vz with a Vx. So we're going to have here Vx squared average plus Vx squared average plus the original Vx squared average. The whole thing is equal to V squared average. So now we can say that V squared average is equal to Vx squared plus Vx squared plus Vx squared, which will give us 3 Vx squared average. Let's now isolate for the Vx squared average on one side by itself, which would be equal to V squared average over 3. Okay, that was a bit fast, but it's required knowledge that Vx squared now is equal to V squared average over 3. Now, why is that important? Because now I can replace the Vx squared average here with V squared average over 3. Now let's simply make this into one big fraction. So we're going to have n m v squared average over 3 times volume. Now that's going to be our equation for the pressure. Pressure is equal to n times m times v squared average over 3v. Okay, now let's talk about kinetic energy for a bit, which equals to half mass times v squared. And if I'm talking about a single molecule, it's v squared, okay? But if I talk about, the average kinetic energy, then I must talk about the v squared average. So if I talk about the average kinetic energy, I must speak about the v squared average. That basically means that the v squared average is equal to 2k over m. That's the v squared average. And now I can replace the v squared average in here with 2k over m. So I'm going to say that pressure is equal to n times m. And instead of v squared average, let's put 2k over m. And the whole thing is going to be divided by 3v. And now what we could do is we could cancel out those m's. Now we're going to have pressure is equal to 2nk over 3v. What this tells us is that the pressure is going to be directly proportional to the value of kinetic energy of K. Okay, let's do this question here. At ordinary room temperature of 20 Celsius and a pressure of 1 atm, how many molecules are there? Molecules will be capital N, and how many moles are there, which is small n. Now, first thing you do here is you have to convert the temperature from Celsius to Kelvin by adding 273, which will give you 293 Kelvin. That's the first thing. Second thing, the pressure is going to be 1 atm, but we should always convert atm to Pascal by multiplying it by 10 to the power of 5. We're going to have 10 to the power of 5 Pascal. The volume is already given to you in meter cube, so keep it in meter cube. Keep it in meter cube. Now they're asking for the molecules. That means I have to go to PV is equal to capital N kBT, and the molecules will be capital N. So I'm going to say that PV over kBT is equal to capital N. Okay, now let's apply the values. So N is equal to, and instead of P, just put the pressure in Pascal. And instead of V, just put the volume in meter cube. And kB is going to be a constant, 1.38 times 10 to the power of -3, provided to you in the reference sheet. And of course, you have to convert the temperature from Celsius to Kelvin. And now my answer will come out to 2.47 times 10 to the power of 25 molecules. That's how many molecules I have. And the second part of the question wants to find the moles. And now you can do PV is equal to nRT. And we're looking for the N, which is the mole. So N is equal to PV over RT. And that means you'll multiply your pressure of 1 atm. Your pressure of 10 to the power of 5 Pascal by the volume of 1 meter cube. R is going to be 8.31. And temperature is going to be, again, 20 Celsius plus 273 to make it into Kelvin. And now my answer will come out to 41.1 mole.